usual, and do the exercises at the very end. So let me show you the tutorial sheet if you haven't seen it before. So if you go to week 7, this is week 7. This is the tutorial sheet for today. As you can see, it's not too long. It's only 4 pages long. So as usual, I will take you through every command in the tutorial sheet, and also do the exercises at the end, right? Okay, guys. So let's begin. Right, before I start, let me there are four R functions that I need to use in this tutorial, and these are, so I'm going to copy them. And paste them in the R session. So to open R, you go into the Start menu, and you go down this, and then you click here and choose the 64 version. Right now, I'm going to paste the 4 R functions. Now, as I go along, I will explain to you what these R functions do, right? And if you have questions, as usual, please use the chat room, right? The first of the 4 R function is called new f.1. Oh, what did I type? NEW. Did I type something wrong? Not found, it says. Oh yeah, I know what I did. I didn't copy it correctly. Okay, let me copy this correctly. Okay. So this is the first of the 4 functions that I'm using, right? Okay, so and this function here is called new f.1. It does the following. What it does is it computes the n-1 times s squared divided by sigma squared, right? For 500 samples each of size n simulated from the standard normal distribution. Okay, so you can see, so it computes the value of this statistic for 500 samples each of size n simulated from the standard normal. So your sigma is 1 basically, right? And you may recall what this, I mean, we talked about this statistic some time ago in one of the videos. I think the video was on chi-square distribution, right? And in that video, I explained to you that, okay, before I talk further, let me say S squared here is the sample variance, right? And sigma squared is the population variance, and n is the sample size. Now, if you look at the video on the chi-square distribution, you will see that this statistic, this statistics has the chi-square distribution with, sorry, chi-square distribution with n-1 degree of freedom. I mean, this is a property I mentioned in the video on the chi-square distribution. If you don't remember this property, just please go back and watch the video on chi-square distribution. Okay. Now I'm going to illustrate this fact that this is a theoretical result, that this result here is a theoretical result. And I'm going to illustrate this using simulation. All right, to do that, the first thing I will do is I will simulate 500 values of, 500 values of this statistic with n equal to 50, right? So this command which I just typed, right, the command that I just typed has generated 500 values of this statistics, 500 values of this statistic with n equal to 50, right? Now, what I want to show you now is that this simulated data follows the chi-square distribution with n-1 degree of freedom. To show that, the first thing I'm going to do is I'm going to draw a histogram of the simulated data with the frequency equal to false. And this is what you will see. So what I have drawn here is the histogram of the simulated data. And the x-axis goes from 20 to maybe 85. So let's define the x to be a sequence from 20 to 85 in steps of 1. Now I'm going to define y as the density of the chi-squared. So it's dCHISQ at x with the degree of freedom equal to n-1. In this case, our n is, you should look above, our n was 50. So n-1 is 49, okay? Right? And finally, I will use the command lines command to draw the density of the chi-squared with 49 degree of freedom. And this is what you get. So as you can see, the theoretical result is justified by simulation. So what I have shown you in this graph is that the density of the chi-squared with 49 degree of freedom matches up the simulated histogram as it should, right? All right, guys, are you okay with this or no? Yeah, does it make sense? Yeah, okay. Now let me repeat this for different values of n. So now in this case, I took n to be 50, right? Now let's choose, say, suppose, let's choose some other value for n, say 20, for instance, right? Then as usual, the next step is to do the histogram, which looks like this. So here the x-axis ranges from say 5 to say 45. So you define the x-axis to range from 5 to 45 in steps of 1, and then you define the y as the density of the chi-square. But here the degree of freedom will be 19 because your n is 20, right? And finally you use the lines command, and this is what you get. Again, as you can see, the density of the chi-squared with 19 degrees of freedom matches up the simulated histogram as it should, right? Now let's try the same thing again with, say, n equal to 100. So I'm going to change here n to 100, right? Then you do a histogram which looks like this. So here the x-axis ranges from 60 to 160. So you define the x to go from 60 to 160, right? And then you define your y to be this. Yeah, you are right, Mikhail. Yeah. So the function new f dot 1 generates 500 samples. It generates, what it does is it generates 500 samples, each of size 50, right, when n is 50. And for each of the samples, it computes, for each of the 500 samples, right, it computes the sample variance. So it computes the statistics, which is this one. So this is it computes this statistics for each of the 500 samples of size n. Right? N can be any number, right? So when I type this command here, when I use this command here, what it does is it computes this 500 times for 500 samples, each of size 50. right? Each of size 50 simulated from the standard normal, right? So you have 500 samples, each of size 50, and for each of those 500 samples, you are computing this statistic. So that's why you see when I type res1, you see there are 500 values here, right? Okay. Any other questions, guys? Is this clear to all of you or not? Any clear? I mean, please feel free. If you have other questions, please feel free to ask me there. Thank you. All right, so this is now the next section of the tutorial sheet is about the sampling distribution of the sample mean and the sample median. Right now, the function I'm going to use for this is the following. It's called new f.to. So what this function does, let me explain. It computes two things. First, it computes the sample mean of 500 samples each of size n simulated from the standard normal, right? And it also computes the sample median. It also computes the sample median for 500 samples, each of size n, simulated from standard normal. So for example, if I type next page, I think it's on page 3, guys. It's on the tutorial sheet. It's on page 3. If I type, say, res2 new f with n equal to, say, 30, right? What you will see is the following. Now, you will see 500 values of two columns. The first column is the sample mean, and the second column is the sample median, right? All right, so the first column gives the sample mean for the 500 samples, each of size n. Here n is 30, and the second column gives the 500 the sample median of the 500 samples, each of size 30, simulated from standard normal, right? Okay, now if you do a box plot of res2, this is what you will see. As you see, there are two box plots here. The first box plot is the box plot for the 500 values of the sample mean, and the second box plot is the box plot for these 500 values of the sample median, right? As you can see, they are both pretty symmetric, right? They are both they are more or less the same, except the variability of the first box plot is slightly smaller than the variability of the second box plot, right? So you can say that maybe the distribution of the sample mean is slightly less variable compared to the distribution of the sample median, right? Because of the length of the box. Remember that the length of the box shows you how variable the data are, right? So the narrow the box is, the smaller the variability, right? As you know. Okay. Now let me okay, in this case I took n to be 30. Let's try different values. Yes, let's take n to be 100, right? And this is what you see. Once again, they are both pretty symmetric. Once again, the variability of the first box plot is smaller, slightly smaller than the variability of the second box plot, right? Now let's take n to be 200, right? All right, now it's the same thing again. They are both symmetric, and again, the variability of the first box plot is slightly smaller compared to the variability of the second, right? Okay, guys. Now, I don't know if you remember that one of the things I taught you when I talked about the normal distribution, I taught you the following. If you don't remember, please look at. Suppose x1 are IID normal with parameters mu and sigma squared, right? All right. Suppose okay. Then one of the results I mentioned in the video is that x bar is the sample mean. In this case, is also normally distributed with the mean equal to mu and the variance equal to sigma squared by n. Do you guys remember this result? This is a result I mentioned in the video on the normal distribution. Right. If you don't remember, please look at it again. Right now, what I'm gonna do now is I'm gonna illustrate this result using simulation, as I did in the first part. Right. To do that, all right. The first thing I'm gonna do is I'm gonna draw a histogram of S2 with frequency equal to f. Oh, what did I do? Oh yeah, it has to be res2 of x bar. Sorry, x bar. All right. So this is what you get. So this is the histogram of the simulated values of the sample mean. Right. Now, what I'm going to do now is I'm on top of this histogram, I'm going to plot the density of the normal distribution with the mean given by mu and the variance given by sigma squared by n. Now remember, in this case, mu is 0, sigma squared is 1, right? So first thing I need to do is to define the x range. So let me take x to be a sequence from minus 0.3 to 0.3 in steps of this, and y to be the density of the normal at x with the mean equal to 0, and the standard deviation, remember sigma is 1, so the standard deviation is going to be 1 divided by the square root of n. Now the n in this case is 200, so it's going to be 1 divided by square root of 200, right? You follow me? And finally, I use the lines command, and you see, this is what you see. So once again, the theoretical result is justified, well, is verified by the simulation that I have shown you here. So the curve I have drawn is the density of this distribution, right? With mu equal to 0 and sigma squared equal to 1, right? And the histogram I have drawn here is the histogram of the simulated values of x bar, right? So they do match up closely as they should, right? As it should, right? Are you guys okay with this or not? Talk to me, guys. Yeah. Okay. Good. All right. Now let me repeat this for different values for n. So in this case, I took n to be 200. Okay. Now let me go back and choose n to be, say, 100. Right. Right. And then I do the histogram again, and the histograms looks like this, right? And I define the x-axis to be this, and the y to be the density of the normal with mean equal to 0 and standard deviation. Now n is 100, so you change n to 100, and finally you use the lines command, right? And once again you see that the density, the plotted density of the normal fits the simulated histogram pretty well, as it should, right? Okay. All right, so this completes the second part of the tutorial. Now the third part of the tutorial sheet is about simulating values of sample mean, sample median, sample variance from a Poisson distribution. So the function I'm going to use for the third part is this one. Now, what this does, let me explain this to you. What this does, it does three things. It computes values of sample mean for 500 samples. So it's 500 samples of size n simulated from a Poisson distribution with lambda equal to 10. Right? And it also computes the sample median, and it also computes the sample variance. So it does three things, right? What it does, it generates 500 samples of size n from a Poisson, and for each of the 500 samples, it computes the all right, part on the basis of which statistic would you, I think I have already answered that, Mikhail. Part five of the exercise is which statistics would you choose to estimate the normal mean in practice? I think the answer to that question is the sample mean, because did I not answer that? The answer to that question, Mikhail, is sample mean, because it has shorter variability compared to the sample median. I think I have explained that in the previous exercise when I did. You remember the width of the box was shorter for the sample mean compared to the sample median. So you would pick the sample mean over the sample median, right? Because the width of the box was shorter. All right. Okay. All right. Now let's get back to this, right? So this function new f dot 3, what it does is it computes the sample mean, the sample median, and the sample variance for 500 samples, each of size n simulated from a Poisson with parameter 10. Right. So, for example, if I type res3 new f dot 3 with say n equal to say 30, right? Okay, and then type res3, this is what you will get. All right, you have three columns of data, right? The first column gives the values of the sample mean. The second column gives the 500 values of the sample median, and the third column gives the 500 values of the sample variance. Okay, as you can see, remember, all right, let me, okay, before I talk about it, let me do the box plot, right? If you do a box plot of res3, this is what you will see. You have the three box plots. The first one is for the 500 values of the sample mean. The second one is for the 500 values of the sample median, and the third is for the 500 values of the sample variance. Now, as you can see, the third box plot is not very useful because it has large variability, right? The first and the second, it's difficult to pick between the two. The second one is kind of weird. The second box plot is kind of weird. The reason for that is, if you look at the data, right? If you look at the simulated data, you see that. Let me show you. Right, if you look at the second column, which is the sample median, it can only take integer or half integer values. The reason for that is because, remember, when we talk about sample median, I think that we did that in the first week of classes. When we did that, the sample median is defined as the middle data point when the data is arranged from the smallest to the largest, right? In other words, the sample median can only take values actually in the data, right? Okay, so because the Poisson distribution, remember the Poisson is a discrete distribution. So it can only take integer values like 0, 1, 2, 3, etc. Right? And therefore, the sample median can only take integer values or half integer values. Right? And that's what you see here. So the values of the sample median are like 9, 9, 10, 9, 10.5, and so on. Right? Because that's because of the fact that the Poisson distribution can only take integer values, and therefore the sample median can also take only integer values or half integer values, right? Okay, so that's the reason that you should look at the box plot, the second one. It looks kind of weird compared to the other two. Right, now let me do this with other values for n. Suppose I choose n to be 100, right? Then in this case, the box plot is kind of similar. Suppose I choose, say, n is to be, say, 200. In this case, the box plot is similar. Once again, you see the middle box plot is kind of weird because of the reason that I explained, that the sample median can only take values that are actually in the data. That's because of the way the sample median is defined, right? Whereas the sample mean is that, I mean, the sample mean can be anything because it's just a simple average of the data, right? And similarly, the sample variance can be anything because because of the way it's defined, right? So if you have to pick between these three statistics, right, you would choose the middle one because that has the least variability, right? Okay. All right, guys. Any questions on this before I do the next part? Are you sure? All of you okay? Or you only one? I like to hear from more of you guys than just one person. All of you guys okay? Thank you. All right. All right. The last part of the tutorial sheet is about simulating from sample proportion from a binomial distribution, right? And the function I'm going to use for this is this one here. This is the function I'm going to use. Now, what this function does, it computes computes sample proportion for 500 samples generated from or simulated from a binomial distribution with parameters n and p. All right. So, okay. And now I don't know whether you remember that. I don't know whether you guys remember when I talked about the binomial distribution, one result that I mentioned, actually, I think I proved this result, is that the sample proportion, when you have data from binomial, right, the sample proportion is approximately normal with parameters p, the mean equal to p, and the variance equal to this. Do you remember this result, guys, or no? This is a result that I proved in the class when I talked about the binomial distribution, right? Yeah, all right. So here p is the parameter of the binomial, n is the sample size, right? Okay. Now what I'm going to do in this exercise is to illustrate this result. This is a theoretical result. Okay, I'm going to illustrate this result using simulated data, right? So the first thing I need to do, right, is to simulate the data. So let's say REST4 let's take n to be, say, 100, and say let's take p to be 0.6, right? Okay, so this is So I have basically simulated 500 values of the sample proportion, right? Now I want to show you, I want to illustrate to you that the 500 values that I simulated can be approximated by a normal distribution with mean equal to p and variance equal to this, right? To illustrate that, the first thing I'm going to do is to do a histogram of the data, the simulated data, and this is what you get. So as you can see, the x-axis ranges from 0.45 to 0.75. So let me define the sorry, I should use frequency equal to false, all right? This is frequency, because the reason frequency should be equal to false is because I want to compare this with the density of the normal. So you should always take frequency to be false, right? Right, now let's define the x-axis to go from 0.45 to 0.75 in steps of say 0.01. And the y-axis to be the density of the normal with the mean equal to p. Remember our p is 0.6. So your mean is gonna be 0.6, and the standard deviation is the square root of p times 1 minus p divided by n, right? And you should look, once again, you should look at our n is 100, your p is 0.6, right? So it's going to be the square root of 0.6 times 1 minus 0.6 divided by n, which is 100, right? So that's the y values. And finally, use the command lines x comma y, and this is what you get. As you can see, the density of the normal is a good match to the histogram of the simulated data, as it should, because this is a result I proved in the class. This result here, that the sample proportion is approximately normal, is a result I proved earlier in the class. If you have forgotten, please look at the video on the binomial, right? You will see this, right? Okay. Now here I have chosen n to be 100 and p to be 0.6. Now let's try with different values, okay? Let's try, say, let's take n to be, say, 200, right? And p to be 0.6. Then you do the histogram, which looks like this. So it goes from 0.5 to 0.75. So you take x to be 0.5 to 0.75, and then you take y. So your mean is gonna be, once again, 0.6, and the standard deviation is gonna be the square root of p, which is 0.6, 1 minus p, which is 1 minus 0.6, divided by n, which is 200, right? And finally use the lines command. And you see once again that the density of the normal is a good fit for the simulated data, right? As you should, right? Okay. All right. Any questions so far, guys? Hello. Hello, guys. Talk to me. Are you all right? Sure. So this is the end of the tutorial sheet for today. And because this, as I said before, it's not the tutorial sheet today is kind of short. It's kind of short, and so it's not so it's easy. Is there anything that you like to ask about everything I have done in this tutorial today? Anything that was not clear, please let me know now. No, are you sure? The whole thing I did today, the tutorial sheet, was it okay or not? Yeah. Okay, thank you. Um, yeah. By the way, this is the last week before the tutorial, before the before the Easter break. So I wish you all of you happy Easter break, and also yeah, I will be in Manchester throughout the Easter break. So if you have questions, on anything I've done covered, please feel free to contact me 24/7 by email or Skype or Zoom or phone. You know my phone number at home, which is 0161 273 2941. I'm also, if you are in Manchester, I'm also happy to meet you in person and talk to you and go through problems with you. Throughout the Easter break, I will be here. So please feel free to contact me. And one other announcement is that the quiz number 6 is due on Thursday. That is the day after tomorrow, by 10 a.m. So if you haven't done quiz 6 yet, please try to do it as soon as you can. And again, if you need help with quiz 6 or any of the other quizzes, please contact me. Okay. None of the quizzes are trivial. If they're all trivial, you would all get 100%. I don't want that. So, but if you need help with any of the quizzes, if you find it too hard or something, please feel free to contact me. Okay. All right. All right. So have a happy Easter and have a good afternoon or good morning or wherever. And I will talk to you soon, guys. Okay. And take care of yourself. Okay.